All right, open up your book to section 15.3. This is on page 767 in your book, and the title of this section is Series and Partial Sums. The objective here is given a series, find a specified partial sum, or find the number of terms if the partial sum is given. Secondly, be able to use sigma notation to write partial sums. And third, given a power of a binomial, expand it as a binomial series. All right. For the second part here, we're going to deal with the differences between what we call a convergent series versus a divergent series. So let's first start out with a definition here of what those two terms mean, converge versus diverge. So for a series with an infinite number of terms, again, a series is a sum of a sequence. And we're talking about a sequence that goes on forever, so therefore our series goes on forever there, and we're adding up all these terms. When we use the word converge or a convergent series, we're saying that the partial sums of that series approach a finite number. So if you calculated, the 100th partial sum, then the 1,000th partial sum, and then the 10,000s, and so forth, you'd find that you keep getting closer and closer to some given number, a finite number. That's what we mean when we say that the series is convergent. The opposite of that is a divergent series. When we use the term diverge, we're saying that we have a series whose partial sums do not approach a finite number. So as you keep adding on those terms, it turns out that the sum keeps getting bigger and bigger and bigger. It keeps increasing without bound. It does not approach a finite number. It's becoming infinite. All right. Let's talk about our two special series here that we've worked with, the arithmetic and geometric. First of all, with an arithmetic series, it does not matter what common difference you have. It doesn't matter how big or how small, whether it's positive or negative. With an arithmetic series, your arithmetic series will always diverge. There's no calculation you got to do, nothing you got to worry about. Doesn't matter how big that common difference is, like I said, it always diverges. With the geometric, it's a slightly different story. With the geometric, it depends on the value of your common ratio r. Sometimes your geometric series will diverge, and sometimes it will converge. So your geometric series is divergent if the absolute value of r could be positive or negative here, so we're saying the absolute value of it, if the absolute value of r is greater than or equal to 1, then it's divergent. On the other hand, if the absolute value of r is less than 1, then your geometric series is convergent. So sometimes it diverges, and sometimes it converges. In the case of an arithmetic, it's always divergent. In the case of geometric, it depends on the value of r. So I guess the next question would be, well, if a geometric series can sometimes converge, then what number does it converge to? Well, it turns out that you can use your partial sum formula to help you come up with this. We know what the partial sum of a geometric series is. In fact, it looks very similar to this little formula that we have here. You'll notice that we're missing the r to the nth power in the numerator, though. But using that, I can come up with this result here. The partial sum of the sum of a geometric series, that is the sum of the infinite terms there, turns out to be equal to p sub 1 times 1 over 1 minus r. I should say it's converging to that number. The sum of your series is the first term times 1 over 1 minus r. All right, so now how do we know that? Well, it actually takes a little bit of calculus for us to prove this, so we're not going to be able to totally prove it. I would call this more of a sketch of the proof. But we'll use this to kind of help us understand why that's the case. But it starts out with using what we already know from a partial sum for a geometric series. So the partial sum for a geometric series we know is S sub n is equal to t sub 1 times 1 minus r to the nth over 1 minus r. And again, if you look at these two formulas, they look almost the same. We're just missing that r to the nth power, as I mentioned, in that numerator. All right, so the question is, what happens as I let n get bigger and bigger and bigger? All right, and the way we'll note that is we'll say n is going to, or approaching infinity. I'll use an arrow there to indicate we're going to infinity. Infinity is not a number, so I can't be equal to it. So we use an arrow mathematically to indicate that. N is going to infinity. It's getting bigger and bigger and bigger. It's increasing without bound. So as n goes to infinity, and we're also going to assume here we're talking about a convergent series here for this. So if it's divergent, then we know that the series is going to infinity. I don't have to calculate what the value is that it's converging to. So if it's converging, then I know that the absolute value of r is less than 1. That was the other property that we just had up above there, that it converges if that's the case. So think about what that means then for that r to the n. The only place I see the n show up there in the numerator of this is the nth power of r to the n. So as n goes to infinity, then what's happening with r to the nth? What's it doing? Well, let's think about that. In fact, let's do a couple of examples on our calculator to help us illustrate this. So grab your calculator. Let's try a couple things out. We're talking about a common ratio that's less than 1, so I'm just going to pick some number less than 1. In fact, I'll pick 0.9. Now the question is, what happens if I raise 0.9 to a bigger and bigger and bigger power? I'm letting the exponent get bigger and bigger and bigger. Like what happens if I raise this, say, to the 10th power? Oh, it gets smaller, right? I get 0.34. What if I were to raise that to the 100th power? Oh, it gets even smaller. That's really small. What if I raise it to the 1,000th power? I don't know if my calculator can even handle that. It does. I get even smaller, right? The question is, what value are you approaching here? And I can see that I'm getting closer and closer and closer to a value of 0 as I do this. So with that, little analysis there, I guess, numerically on a calculator, that should kind of help convince us. Again, this is not a formal proof, but more of a sketch of a proof here for us. But that should help convince us that as n goes to infinity, and if your common ratio, the absolute value of it's less than 1, then r to the nth power is headed towards 0. It's approaching 0. So, what does that mean then? So if we're trying to calculate the sum here, S sub n, I shouldn't say equals, we're saying we're going to let n go to infinity here. So S sub n takes on the form of t sub 1 times 1 minus r to the nth over 1 minus r. And again, we just said that if we let n go to infinity, that this thing right here is disappearing. It's becoming 0. It drops out of here. So in other words, this takes on the form of t sub 1 times 1 over 1 minus r. And that right there is our formula. And we'll call this S. This is equal to S. This is the sum of that series. That's what the series converges to, that value right there. All right, so let's try using that in a example here. Look at the example on page 470, or sorry, on page 772. Example 4 on 772. It says, to what limit does the geometric series 50 plus 45 plus 40.5 converge? Well, we'll answer that first. There's a couple of questions that they are going to ask us here, but let's start with that. And just like we've done for all the previous problems, dealing with sequences in series here. Let's make a table of these values. I know they did tell us it's geometric, so that's a big hint, but if you do this each time, that kind of gets you in the practice of doing it every time, even when you don't know what the sequence is, so you have a place to start. So our values are 50 and 45 and then 40.5. So they did tell us it's geometric, but they didn't tell us what the common ratio is. So to calculate your common ratio, by the way, you take the next term divided by the previous term as the ratio you're going to calculate. So this is multiplied by 45 over 50 is what I'm calculating here. Take the 45 divided by 50, and what's that equal to? 0.9, right? And then if I check this guy right here, if I compare the 40.5 divided by the 45, that ratio, take the next term divided by the previous term, that gives you also 0.9. I'll let you punch that in your calculator and verify you get that 0.9, but that's what we should get. 0.9 is our common ratio. All right, so we have a ratio that's less than 1. The absolute value of our ratio is less than 1. So with that, we should be able to come up with what this converges to. Our formula, therefore, is equal to this. Let's make that note there. Since R is equal to 0.9, that is, the absolute value of R is less than 1. That's the key there. That tells me that the series converges. Now again, the question they asked was already leading us to that because they said, tell me what value it converges to. But this is how I know that it converges. Look at the common ratio. Since it's geometric and the common ratio is less than 1, we know it's going to converge. All right, so what value does it converge to? Well, let's use our little formula here. S is equal to, it's the first term, which was 50, times 1 divided by 1 minus the common ratio, which is 0.9. What's that turn out to be? Well, this is what? 50 times 1 over 0.1. Dividing by 0.1 is the same as multiplying by 10. So this would be 500. So this converges to a value of 500. All right, that's the first part. Second part of this is how many terms must be added in order for the partial sums to be within 1 unit of that limit. So if I want to be within 1 unit of 500, that means that I want to be at least 499. So the second part of this, maybe I should call this part A and part B here. This is really part A, we'll say. This is part B down here. I'm trying to find out when my partial sum is greater than this 499. I want to be within 1 unit of that answer. If you want to say it's 500 minus 1, same thing. But I want to find out when it's greater than 499. Well, let's write down our partial sum then. 50 times 1 minus 0.9 to the nth power divided by 1 minus 0.9. I'm going to, again, change this to equals. If you want to keep the inequality, there's nothing wrong with doing it that way. You just got to deal with when I multiply or divide by negative numbers and switching that properly versus with the equal sign, I don't have to deal with that. So I'm going to write it as an equality here. All right, so let's simplify this. Well, we've already dealt with dividing by the 1 minus 0.9. That's the same as multiplying by 10. So really what I've got here is 500 times 1 minus 0.9 to the nth power is equal to 499. So let's divide by the 500. 1 minus the, so I want to keep putting a 1 out in front of this thing. 1 minus 0.9 to the nth power is equal to 499 divided by 500. And now let's solve for the n. We've done this now several times, so hopefully we're getting the hang of this. This is going to involve logarithms to do it. So I've got, maybe I'm going to write it this way actually. Let me move the 0.9 to the nth power to the other side so it becomes positive, and I'll subtract this guy here. So I've got 1 minus 499 over 500 equals 0.9 to the nth power. I guess that's a little different than how we've done some of the others, but nonetheless, when I subtract these two on the left, I get 1 over 500. That's easy to subtract then. All right, now we're at the point where we use logs to solve this, right? Take the log of both sides, use your power property, bring the n out front, and so forth. So let's do that. Log of 1 over 500 is equal to the log of 0.9 to the nth. And again, our property here, our power property for logs, lets me bring this n out front. We'll write it that way, and then we'll solve for n. So we've got the log of 1 over 500 equals n times the log of 0.9. And finally, to solve for n, let me put the n out front here. I guess we'll say n is equal to, dividing by the log of 0.9 gives me the log of 1 over 500 divided by the log of 0.9. Those are both negative numbers, but when I divide them, I'm going to get a positive number here as a result. Let's see what value we actually get here. So grab your calculator and let's try that. So I've got the log of 1 over 500 divided by the log of 0.9. And so we get, what, 58.984. Guess I'll grab a picture of that. All right, so we end up with n is equal to 58.984. But again, we got to round up to the nearest whole number. That's what our domain is here, is whole number. So n must be equal to 59, it looks like. So until you get the 59th term in there, that finally is within 1 unit of 500. So it takes quite a few terms to get within 1 unit. All right, that right there is the end of part 2 here of section 15.3.